Two platforms, nearly identical transistor counts. One delivers more than twice the inference throughput per watt at the tactical edge. The other can be sourced from 4 different foundries across 3 continents. The question is not which one is better. The question is, which integration architecture survives the constraints you have not stress-tested yet, and what do you trade to get there? The horizontally integrated platform model has defined commercial edge compute for a decade. You source the application processor from one vendor, the modem from another, DRAM from a third. The operating system stack sits above all of it, negotiating across multiple bus interfaces. On paper, this is resilience, 4 foundry options, no single vendor dependency, procurement flexibility. The architecture looks distributed, multiple nodes, multiple paths, but look at the seams. Every boundary between discrete components carries a latency and power penalty. The LPDDR5 bus between the AP and the memory stack runs at 64 GbS under ideal conditions. The interface to the modem adds 3 to 5 microseconds per transaction. Each seam is a toll gate. The system appears resilient. It is not. The flaw activates under 3 concurrent conditions: thermal constraint, reduced power budget, and active inference workload. Under nominal lab conditions, the horizontally integrated architecture performs within 15% of a vertically integrated equivalent. But at 35 degrees Celsius ambient with a 5-watt power cap, the thermal envelope for most man-portable and wing-mounted edge systems, the memory bus becomes the bottleneck. LPDDR5 at reduced voltage clips to 44 GbS. The NPU, whose scheduling model assumed full memory bandwidth, starts stalling. Inference latency on a 7 billion parameter quantized model jumps from 180 milliseconds to 340 milliseconds. That is not a performance regression. That is a mission capability threshold crossing. The system did not fail. It degraded gracefully below its advertised specification into a range where the capability it was acquired to deliver no longer exists. The acquisition document said nothing about behavior at 5 watts. The numbers are not contested. Unified memory architecture, where CPU, GPU, and NPU share a single contiguous memory pool without discrete transfer overhead, eliminates the bus penalty entirely. At a 5-watt power envelope, a unified memory platform sustains 94% of its nominal memory bandwidth. The discrete architecture sustains 61%. That 33-point gap compounds through the inference stack. For a 4-bit quantized model at the edge, the difference is between a system that classifies a sensor fusion frame in under 200 milliseconds and one that cannot. One makes the latency budget for the fire control loop. One does not. The foundry sourcing column is the only dimension where the horizontally integrated approach holds a clear advantage, and that advantage is real and should not be dismissed. The fix is not by the vertically integrated platform. The fix is to separate 2 decisions the commercial supply chain has conflated: silicon architecture and foundry sourcing. A vertically integrated silicon design, where application processor, neural processing unit, and memory controller share a unified fabric, does not require a single foundry. The architecture and the manufacturing are separable decisions. Domestic foundry investment under the CHIPS Act and the Chiplet Interoperability Program under DARPA's Jump 2 initiative both point in this direction. Design the integration architecture as a vertically coupled fabric, then qualify that fabric across multiple foundries. You retain the bandwidth characteristics of unified memory without the geopolitical single point of failure at the Taiwan Strait. Implementation cost is real. Multi-foundry qualification adds 18 to 24 months to program schedule and demands a design team capable of managing process node variation across fabs. But the alternative is an edge compute platform that silently crosses its mission threshold when the power budget tightens in the field. Name what you trade. Multi-foundry qualification for a unified memory fabric is not a standard program increment. You are looking at 18 to 24 months of additional schedule, a design team that costs 40 to 60% more than a standard integration shop, and a test and characterization burden that commercial programs do not carry. The power efficiency gains are real and measurable. The supply chain resilience is real. But you are also now the system integrator for a chiplet-level architecture that has no commercial analog and no existing COTS vendor to absorb program risk. The software stack is simpler, one unified hardware abstraction layer versus a multi-vendor driver stack. But your certification pathway under DO 178C or MIL STD 882 runs longer because the architecture is novel. Every trade-off in this space is real. None of them are symmetric. The integration seam is not a hardware problem. It is an acquisition architecture problem. Every program that sources discrete components without specifying bandwidth behavior under constrained power has already made the choice. They just do not know it yet. The specification said 64 gigabytes per second. It did not say what happens at 5 watts. The question is whether you find that out in the lab or downrange.